Follow Shadow Junior Twin.
Hello guys, so today we're covering the sorting algorithms, which is really the last of the stuff that you could have covered at GCSE level. Um, because next we're going over Big O, which is going to be very interesting. We can now cover Big O because we've covered all of the searches, sorts, and I guess the trees, but the trees don't really have a very significant part of Big O. So we're going to cover Big O, and then we're going to cover the trees, and we have 133 days left until paper one. Quite a lot of time. We're on very, very, very good pace. Paper two is going superbly. Anyways, what four sorting algorithms do you need to know? Maybe you can answer that before I go onto the slide and actually tell you, but I'll give you a couple seconds to think about it. Here we go. Bubble sort, insertion sort, merge sort, and quick sort. Now, you need to be aware of the pseudocode for both these two here, more so the bubble sort than the insertion sort, but if you're aware of the pseudocode of these two, you'll be quite covered. If you know how to do it, then you know how to answer any question because you know how to explain it, you know how it works, you can describe it, all of that stuff. The merge and quick sort, you don't actually need to know the pseudocode for. You wouldn't have to do a skeleton for it. You just need to know how they work and how you can actually perform them. You don't need to know how to program it, but you need to know how to actually do it yourself. So, let's start off with the most primitive and simple one in my opinion, because I rank these in order: bubble, then insertion, then merge, and quick, to actually understand. But I think the bubble sort is the most intuitive one. You know how for the searches I said the linear search is the one that you might think of when you think of how to sort a list? I think the bubble sort is an example for this one. So the bubble sort works by just comparing items. You're comparing items to see if they need to be swapped. And if they do, you swap them. Otherwise, you don't, and you move on to the next items in the list. And you repeat this until you go through the list while no swaps occur. And when that happens, you know the sort is finished. So what does this actually mean? Let's go through an example together so we actually know what I'm talking about. And we're trying to sort this list here into ascending order. Now you obviously can very clearly see that it'll be 1, 2, 3, 5, but let's see how the bubble sort does it. So this is pass one. We're going to act out all of pass one. And sometimes you don't actually have to write out every step in pass one. You might have to write out what happens at pass one, then pass two, then pass three, then pass four, and then pass five it finishes. But sometimes they'll be like, okay, write out a full pass of the bubble sort. We will write out every swap in the bubble sort, but only one pass. I doubt they would ask you to write out every pass with every step in it. But anyways, let's go through pass one. So we compare index 0 and 1, and we see that 1 is less than 2, and we're trying to get it into ascending order. So we're going to swap them. And then we move on to the next indexes. We compare 2 and 3, no swap, 3 and 5, and no swap. And we've reached the end of the list, meaning that we've finished this pass. So you would have to go ahead and do pass 2, but I haven't done it here for spacing, but we know this is a sorted list. So we know in pass 2 there's going to be no swaps. And with our definition earlier, this repeats until there's a pass with no swaps, meaning we're going to end at pass 2. Pass 2 does still happen when you do the bubble sort because you need to have that case. And we're going to see that in the pseudocode in a second, but I did that for space here. You would do another pass and you would say that there's no swaps. So, what actually does the pseudocode look like? So if we just have an array up here, which stores 5, 4, 3, 2, 1, which is actually the reverse order of what we need, which is kind of annoying, but we'll see how the bubble sort does it. So you know how we have to keep track of how many swaps we've made to actually check if we've finished the algorithm? We can do that by having a Boolean variable. It can be called anything, but we set it to true initially. I'm going to go through why we do that. We then set our index to be 0 because we want to start at the start of the list. And then we have a while loop here. While swap check equals true. So while we have swaps present in a pass, we're going to repeat. This code here represents a pass, right? So while this swap check is true, we're going to carry out and do another pass. Because if a swap's happened, we're going to do another pass. We established that earlier. But as soon as we start this while loop, we need to set swap check to be false. We need to show that there's no swaps that initially happen. When you start a pass, nothing has happened, right? There hasn't been any swaps yet, so you set it to be false. At the start of this pass, although we have a swap straight away, right here, there hasn't been any swaps yet. So we set swap check to be false. And if this remains false all the way through the pass, this while statement will be broken and we finish the sort. So what is this while statement here? We have a nested while loop, which will tell you a bit about what the worst case time complexity will be, but we'll go over that in a second. So while index is less than the length of numbers minus 1, what does this mean in the case of this list up here? Well, the length of numbers is 5, minus 1 is 4, So it's while index is less than 4. So we're only actually going through 0, 1, 2, and 3. We're not actually going into this index here, index 4. Well, why are we doing that, right? Well, it's because of this bit here. We see this if statement. We're checking index plus 1. So if we went to this final index, index plus 1 is outside of the array. Considering we're comparing two adjacent indexes, we only need to go up to here because we're then comparing it to this index here, if that makes sense. So we're checking if numbers index is greater than numbers index plus 1. So let's see what this means when index is 0 and we're in the first pass. We're comparing index 0 and 1, so 5 and 4. Is 5 greater than 4? That is true. So we're going to carry out this code here. So we're saying swap check equals true because a swap has occurred. We do have to, this means that this loop is going to continue because a swap has occurred. And then we have to actually just go ahead and swap these indexes, swap these items. But how do we do that? We need to create a temporary variable to swap the indexes, right? If we don't create a temporary variable and we overwrite this index with this data, well, how are we going to place the 4 into the 5 if both of these are now 5, if that makes sense? We have to create a temporary variable which allows us to actually swap the data. Hopefully that makes all sense. And then this while loop will then continue and continue and continue until you reach the end of the list. And then if this is true, we're going to go again, set it to false, reset the index to 0, because remember, at the end of a pass, we need to go back to the start of the list to do the next pass, and then go back again. So we need to reset index to be 0. Hopefully that makes sense. So now we're going to go over, you could optimize the code actually. So one way you could optimize this code is, after you carry out a pass of a bubble sort, for example, this number 5, after one pass, it's going to swap with 4, swap with 3, swap with 2, and swap with 1. And it's now at the correct index. It's the greatest number in the list. It's in its correct place. And after the second pass, 4 is going to swap with 3, 2, and 1, and it's going to be in its correct place. So you actually only need to do n-1 comparisons for each pass, and that's going to decrease by 1. You need to do 4 comparisons at first, then 3 because this is in the correct spot, then 2 because these two are both in the correct spot, the 4 and 5, and so on and so forth. So this while loop could actually be optimized, and it's not too complicated to do, but this is only a slight optimization. The time complexity of bubble sort is still the same. So what actually is the time complexity? And we mentioned the nested loops beforehand, so let's go over the worst case time complexity, which is O of n squared, and because we have the nested loops. And this is also equivalent to the average case time complexity. So both the worst case and average case time complexity is O of n squared, which is quite bad. That's why the bubble sort is quite bad. Typically, the worse the sort is, the easier it is to implement, right? The insertion sort and bubble sort are quite easy to code, but they're way worse than the merge and quicksort, which are quite difficult to code. And that's typically the trade-offs we need to consider when we're thinking about long-form questions. You know, why is something quicker? Is it there has to be a trade-off. If it's quicker, is it harder to implement? Is it more expensive to implement? As in more space complexity and more variables need to be tracked, stuff like that, you know? So what the best case time complexity of the bubble sort is O of n. If the list is already sorted, only one pass is necessary because no swaps will take place and the sort would just end. But you still need to go through every index in that list, so it would have a time complexity of O of n. Well, you need to go through n-1 comparisons, but that's the same as O of n. So we're going to cover space complexity when we cover big O, so we're not actually going to go over the space complexity of the bubble sort at the moment, but we're going to cover that in the next video. So now moving on to the insertion sort, which kind of builds upon the bubble sort, and the fact that it actually uses a bubble sort when it's placing indexes into the correct position of the sorted list. But let's first define the insertion sort. So it works by partitioning the original list, that's array, into two lists, a sorted list and an unsorted list, right? And data in the unsorted list is then placed into the sorted list. Placed in order into this? Yeah, in order into the sorted list. Initially, the sorted list has a size of 1 and contains the first value in the original list. So that's our definition of the insertion sort. But same thing for the bubble sort. Let's go over an example of how it actually works. So we have the exact same list as before, and we're going to sort it into ascending order. So how do we do this? Well, this line here marks the split. It marks the sorted list and the unsorted list. And no matter what the first index is, it's always going to be sorted because it only contains one element. So this marks the sorted list and this marks the unsorted list. So what we want to do is we want to place this element 1 into the sorted list in its correct position. So what we would actually do is we compare 1 and 2. Since 1 is less than 2, it goes to the left of 2. And that's our first, I don't want to say pass, but that's our first comparison. That's our first element placed into the sorted list, right? 1 is placed in the sorted list using a bubble sort. Now, we need to place the next element into it, which is 3. It slots in quite nicely. 3 is greater than 2, so it slots in very nicely. And then we do 5. 5 slots in very nicely because it's greater than 3, and it's done, right? Once every item has been placed into the sorted list, and the unsorted list has a size of 0, we finish the sort. What does this mean in pseudocode? Now, the pseudocode is quite a bit more complicated because it maybe isn't obvious to see what's going on when you first just have a little glance at it. Let's actually go through this function and let's actually talk about how it works. So as you can see, the first thing we're doing is we're looping from number to be 1 to the length of numbers minus 1. We still have that same thing as before, length of numbers minus 1. So it's looping through to index 4 here. And we're going from index 1, not index 0, right? Because remember, index 0 is the sorted list. This is the case for any list because we're partitioning it like this initially. We're splitting it here. The first index is in the sorted list no matter what it is because there's only one thing in it. So we're looping through these and we're trying to place them into the correct spot. So the key, or what we're trying to place into the sorted list, as we can see here, is set to numbers in the index num. So the first key is going to be 4 because we're trying to place it into here. And the comparator is a pointer. It's pointing to whatever is at the end of the sorted list, which is initially 0, right? Num starts as 1, so comparator is set to 0, and this is what we're comparing the key to as we're inserting it into the sorted list. So what does this while statement mean? Well, while comparator is greater than or equal to 0, while we're moving through and we haven't reached the end of a sorted list, and key is less than numbers comparator. If this number here is greater than the comparator, it can just be stuck on the end of it, right? But if it's less than it, it has to move into it, right? So we have to move this up 1 and we have to move this down 1, right? So while this is true and key has to keep moving down and down and down the sorted list, we have to carry out these swaps, right? We're setting numbers comparator plus 1 to be numbers comparator. So we're setting this index to be 5, and then we're reducing comparator. So comparator is now, well, now it's going to be minus 1. Yeah, so the comparator is now minus 1 because it started at 0. But we're setting numbers comparator plus 1 to be the key. So now we're setting numbers 0 here to be the key, which is 4. So what we essentially did in this first while loop section is we've moved 4 into the sorted list by placing it here, and we've moved 5 to this index. Now, the sorted list now has 2 elements in it. It has 4 and 5 because 4 and 5 are both in their sorted positions. So that's the end of the while loop. This while loop will loop for every single element in the unsorted list because of the for loop we've established here, and they're all going to be placed into the sorted list using this comparator. Now this algorithm is really cool to me because of the while loop. It's a really nice one, very clean, but you need to really understand what's going on here and actually break down the code to know how it works. So hopefully I've explained that to a decent degree and you can understand it. If you don't, check out Geeks for Geeks. It is a great resource, and I think I mentioned it later on in this video. So next, what is the time complexity of the insertion sort? So let's go back. The time complexity is actually the exact same as the bubble sort. The worst and average case is both O of n squared, and the best case is O of n. So, why is that the case? Well, why is the worst case O of n squared? I've derived this in my TikTok actually, so you should go check out my TikTok if you want to see that. But let's go back here. When we insert an element into the sorted list, we're doing a bubble sort. We're comparing the elements, and if not, we're swapping them. So if this element needs to be placed to the front of the list every single time, we're just doing a bubble sort for each element, and we're doing that n times. So the worst case is O of n squared, and the best case is the same. So this is good for comparisons. You can say that the insertion sort has a very similar, well, not similar, it has the same time complexity of the bubble sort. So they're quite indifferent whether you implement the insertion sort or the bubble sort. So, however, we know that big O actually isn't as accurate as it seems because it applies to very large values of n. And on average, the insertion sort will execute slightly quicker than the bubble sort. Um, so that's actually something we'll look into more when we look at big O, because big O just takes the highest contributing um, term, right? And the highest contributing term is n squared, but there's also like n squared minus n, but that minus n is discarded. But we're going to talk about that later on. So, moving on to the merge sort, which is nice. The merge sort is actually technically nicer than the bubble sort and insertion sort because you don't need to know the pseudocode for it. You just need to know how it works and how to perform it on a list. So, how does it work? It takes a list and it splits it until you reach a list of size 1. And then they are merged together into sorted lists until you reach a fully sorted single list. Now, this is a bit of a summary of how it works. We're going to go over a written exam question at the end of this video, which actually involves describing how the merge sort works. So stay tuned for that. So, a quick example, the exact same list. Let's go through it. So it splits this list into two lists at first, right? Because it has a n of log n time complexity. It's splitting each list into two, and then it splits these lists into two again, right? And now it's fully split because we have lists of size 1, as previously mentioned. So we do this until we have lists of size 1. And then we need to merge it back together. We need to merge the same way that we split it. But as we're merging them back together, we are ordering them. So we merge this into this, but we now order it to 1, 2. We have 3, 5, the exact same. Then we merge these two lists together, ordering them to 1, 2, 3, 5. So you do not need to know how to implement a merge sort in pseudocode. And I feel like showing you it will actually just confuse you because it is quite complicated. But if you are curious, check out the Go Geeks for Geeks. It will explain and it does it quite well. So check out Geeks for Geeks if you're curious how to implement a merge sort. I might just do it for why not in one of my videos. Anyways, you do need to know the big O for the merge sort. So we're going to cover that right here. So the worst, average, and best case time complexity of the merge sort is O of n log n, which is really good. It's a well-rounded algorithm. It's very consistent, right? Which is a good thing. You want your algorithm to be consistent. You want it to perform just as good as it does in the best and worst case scenario. Because in the worst case actually isn't that bad. And because of these consistencies, using the big O of the merge sort and the bubble insertion sort, you can compare why you would use different sorts in different scenarios, right? Because on a shorter, partially sorted list, a bubble sort may be better, as its best case is O of n, while the best case of the merge sort is n log n, which is worse than O of n. But on a longer list, the merge sort will be much better, as its time complexity is n log n compared to an average case of O n squared for the bubble and insertion sort. And these questions come up. There was a 9 or 12 marker on comparing the uses of merge, insertion, and quick and the bubble sort on the 2021 paper 2 past paper. I'm going to go over the long form questions entirely on a completely different video. Although this applies very closely to this topic, I'm going to go over it in its own individual video, which I think will be quite good to do all of those 9 and 12 markers in their own video. The quick sort. Moving on to the quick sort, and let's go over how it works. So I think it is the most difficult algorithm it is the most difficult to program, but I also think it's kind of difficult to understand conceptually. But it works by selecting a pivot value, and it does not matter how you select this pivot, as long as it's consistent. But then you place all the items in the array, either to the left of the pivot, or to the right of the pivot, depending on whether it's less than or greater than the pivot. And then after this, a new pivot is selected, and this occurs until every single element has been a pivot and it's finished. That's how we know in the quicksort it's finished. Let's go for an example. So exact same list. I know, a bit boring now, but we're going to do it just for consistency reasons. And we start off by selecting a pivot. Now, sometimes you select the first node to be a pivot. Sometimes you select the midpoint. That's what I've done here. But I select 1 as the pivot, and I move everything that is to the greater than it to the right of it, which is every other element in the array. So now I select something else as the pivot, which is 2, and there are no swaps are made when you select 2 as the pivot, which means that the list is in the correct order. But the quicksort only ends once every node has been selected as a pivot. So we actually have to continue. We have to select 3 as a pivot, and then 5 as a pivot. I don't know why there's 4 in here. That shouldn't be in here. I guess I got so excited with like the order of 1, 2, 3, 4, 5. I had 4 for no reason, but this is what it would look like. And then all nodes are pivots, and we're finished. So, what is the best and average case and worst case scenario for the quicksort? So the best and average case is the same as the merge sort, which is just O of n log n. So it is very similar to the merge sort in that aspect. However, the worst case is O of n squared. which is quite bad, right? That's the same worst case scenario as the bubble and insertion sort. Um, and why is this the case? Well, I derived this on my TikTok. Go check out the video. I'm quite proud of that video. If you're curious, I derived it there. You don't actually know how to derive these. You just have to memorize them for the tests. And I'm in my big O video. I'm gonna have a table of all the algorithms and all their worst, best case, average case times complexities. So stay tuned for that. So this website is amazing. If you want to conceptually see the sorts as executed, it may make it easier to understand them. So check out this website. I'm going to use it myself in a second. Then after that, we're going to go to do some exam questions, right? But first, let's check out this website. So let's do a quick sort. We're going to sort it, show depth, and we're going to increase the speed a bit. So this is the pivot selected pivot. It swapped it. We have a new pivot, swapped it. New pivot. It's going a bit quick, but hopefully you can see that every element has been selected as a pivot, and it's moving all the elements in the correct space as they're being selected as pivots. So if we do that at a slower speed, maybe we can see that a bit better. Compare it to 49, less than, less than, less than, less than, less than. Everything's less than it. So 49 is just placed at the end. Now 0, number sets to 4, and everything's less than it. So this at the end, this is at the start. I'm fumbling over my words right now, sorry guys. And if you saw there, a couple elements were less than it, a couple elements were greater than it, right? This is less than, greater than, greater than. So it gets placed around the middle. And then obviously this continues till everything's selected as a pivot. So on and so forth. Let's speed this up a bit. This also works with a quick sort, a merge sort. See how it splits down, compares, merges, splits down, merges. Now the video doesn't just do it how we're supposed to do it in the exam, but it does the same thing, right? It's splitting it down to list size 1 and comparing them and then merging them all together. And then let's look at the bubbles. Boom, 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 boom. That's 1 pass. 2 passes. 3 passes. 4 passes. 5 passes. 6 passes. And see on the 6th pass there was no swap, so we just stopped. Now let's look at the insertion sort. Here's the sorted list, and everything's being placed into the sorted list in the correct positions. Very cool website. Check out yourself if you're confused. It has the pseudocode here and how it works as it's running. So very cool video. But let's go over to the good notes and do the exam questions. So show how an insertion sort will sort the given data into ascending alphabetical order. Now this is actually quite tedious to do. I'm gonna have to rewrite out rainbow, moon, sun, stars, cloud, and tornado like 10 times. So I'm gonna pause the video and just do it quickly, and then I'm gonna talk over it because you're just gonna be bored if you just sit here watching me do this over and over again. Alright, so I've just gone ahead and done the question. This is such a brain rot question. You just gotta spend 5 minutes writing words over and over and over again. It's just really draining, but it's really, really piss easy, right? You start by positioning it into a sorted and an unsorted list. And remember, the first index is always sorted no matter what. And then you have to place all of these indexes into the correct spot. M becomes before R on the alphabet, so it goes before rainbow. And then sun goes there, stars goes there. Goes before sun because T comes before U and the first letter is the same. That's like the only thing that could potentially catch people out. But if you can do all of that, then it's really just 3 marks. Like the marks just come and you just love it, right? This is 5 3 marks. There's a pause moment there, but those are 3 marks which you should just get, right? These are give me marks. These are the marks that will carry you through, and you don't actually have to think. You just have to do over and over again. So what's the next question? Describe how a merge sort works. So this is also, I don't know whether I think I'm just gonna do the question quickly and then I'm gonna talk through my answer because otherwise this video is gonna be 35 minutes long. I don't want it to drag on for you guys. So I've written up my answer and let's actually just walk through what's going on and then we're gonna look at the mark scheme. So we're splitting the list into 2 and repeatedly doing this recursively until you have lists of size 1. Then you merge these lists together by selecting the smaller of the first elements of the 2 lists and write it into a new list, right? So if we have a list, I don't know, let's say 1, 2, and we're merging that with the list 3, 4, we're selecting the first elements and we're selecting the smaller one and writing that to a new list. Then we're selecting 2 and 3, the smaller one to a new list. 3, and then we just add 3 and 4 because they are the only things remaining, right? That's how it works. And then once that happens, we repeat this until the list is fully merged. Repeat this until all sublists are merged. So let's go look at the mark scheme. Just down here, the data is split into 2 lists. Nice. These sublists continue to be recursively split. Cool. Until each sublist is 1 item. That's 3 marks already. 3 out of 5 marks for just writing 1 sentence. The mark scheme is really nice if you know what you're talking about. The first element in 2 different sublists is compared. Cool. The small item is then selected and written to your list. We've already got 5 marks. We've got the first 5 bullet points, the first 5 marks. Very chill question. So if you know what the definitions are, these questions are really, really free. So give one benefit and one drawback of the programmer using a merge sort instead of a bubble sort. Well, the benefit might be better time complexity, right? Better time complexity. O of n log n versus, obviously this isn't how you write it in the exam, but I'm getting my point across here just for the video. So the drawback might be it's harder to implement. It's harder to code the merge sort, which is actually a practical thing you have to think about. If you're on a time constraint and it's harder to program, you might not be able to get it done compared to a bubble sort. I mean, it wouldn't take you that long to code a merge sort, but it is harder to implement, right? More difficult to implement, boom. More efficient time complexity, right? And this is in brackets, so we don't actually need to write this. So then again, that's another 2 free marks. You really love these type of questions. Okay, now carry out a merge sort on this data. So I'm gonna do the same thing. I'm gonna pause the video, do it myself, and then walk through my answer and compare it to the mark scheme. So boom, I've done it. Couple minutes. These are really free marks because if you know what you're doing, you just have to repeatedly do a bunch of boring stuff and you're getting 3-4 marks. So first things first, you split this in half, bosh, right down the middle, and we have 2 arrays. We're going to split these arrays again in half, here and here. I'm going to keep doing this until we have arrays of size 1, which marks the end of our splitting section of the merge sort. We're then going to merge them back together in their correct order. So we merge 2 and 12, 1 and 9, 3 and 5, 7 and 15 in their correct order. And then merge these back together, merge these back together, and then merge these back together to get something that looks like this. So, splitting into individual items, that's 1 mark, combining in pairs, merge pairs, and then you have a final answer. So you get only 1 mark for splitting fully correctly, but that's kind of chill. That's really not really something to worry about because it's very simple and easy to do, and then you get the other marks for merging it back together. So, very chill 4 marker. And here we have an actual skeleton question. So we're going to go through this together, and then the mark scheme in a second. So a bubble sort will sort an array of 50 integer values called number array. State why the integer values are stored in an array instead of separate variables. Now this actually is a very free 1 mark if you know what it's asking you. So it's asking you, let's say you have an array and it has 1, 2, 3, all the way up to 50. Why is this better than storing num1 equals 1, num2 equals 2, and so on and so forth, all the way up to 50. Why is this a better option? Well, you can access all 50 numbers with 1 variable, right? 1 variable, 1 pointer, same thing. You can use 1 pointer to traverse through the array and access all the numbers rather than just accessing each of the individual variables, right? Can refer to all 50 only using 1 identifier. So yeah, we can access any index just using 1 thing. Okay, now let's go through this skeleton for the bubble sort. And this bubble sort algorithm is written to sort number array, which we're told has 50 integers. So know that array length is going to be 50. Give me mark. Into ascending numerical order. So we're trying to put it into ascending order, not descending. Temp value equals 0. Which is, okay, cool. We're doing this. Look at the flag. And blah, blah, blah. So this is something we have to think about, and this will catch people out. This is 2, not 1. Because if it was 1, it would go to number 49. Array length minus 1 is 49. So it's going to go to index 49. an index 49 is going to be the last index of the array, right? The array stores 50 numbers. We start counting from 0, so it goes 0 through to 49. But as you can see, remember with the bubble sort, we check index and then index plus 1. So I and then I plus 1. So since we're doing I plus 1, index 50 doesn't exist. We need to go to index 48 and then compare that with 49, and we're doing that with the plus 1 here. So we actually need to go to array length minus 2 rather than array length minus 1. So now what we're doing, if number array then we're doing the swapping. And remember, the swapping requires temporary variables, which is actually established for us earlier, which is really nice. Then we do number array y equals number y plus 1, number y plus 1 equals temp value, which we establish here, and that's just carrying out our swaps. So the mark scheme, 50, nice, minus 2 instead of minus 1, temp value, y, temp value. Beautiful question, done nice and quick, 3-5 marks. Oh, almost forgot to circle this one here. Come on, we're getting all the marks. Okay. Describe how Quicksort would sort data into this last question. Yeah. So then again, I'm going to pause this, go through it, and then go through the mark scheme, because this is going to be way too long otherwise. So this is our answer here. The pivot is selected and all data is placed left if less than pivot, or right if greater than pivot of the pivot. After this, a new pivot is selected and this process repeats until all elements selected as pivots. So let's look at the mark scheme. So choose a pivot, boom, compare each element to the pivot, put item left to the pivot in the left sublist, right sublist. So this is already 4 marks secured, with like one sentence basically, 4 marks secured. And then we talk about sublists here because it's technically a recursive process where sublists are created and then pivots selected within the sublist. But we get the 5th mark anyways when you talk about repeating the process until each item becomes a pivot. So that's easy 5 marks. You can get into the specifics with the sublist, which might be useful, but there's always going to be these marks here and these marks here at the end to secure the nice and easy 5 marks. So hopefully these exam questions showed you that getting all these marks actually isn't too hard if you know what's going on. These questions aren't hard to do and they aren't hard to explain. You just have to know what's going on, and then they're actually really easy. Getting the marks is really, really easy. So, thank you for watching.